Hello and welcome to the third lecture in 22nd chapter of our comprehensive course on machine learning, data science and artificial intelligence. Now here we are doing at present this part, that is data pre-processing for machine learning. And in that first part we have completed creating new features, and now we want to do this part, data scaling and normalization. Now as such we had done a lot of discussion about data scaling and normalization in 12th chapter also. You can see that here data scaling and normalization is discussed in a lot of detail. But at that time it was a kind of compulsion, because the other topic which we wanted to discuss that required normalized data. So that is the reason why I had to introduce the normalization at this point. But now we want to do the study of this normalization in even more depth. So let us take one is standard scaling, another is min-max scaling. Now this min-max scaling also sometimes is written as normalization, but I would not prefer to use this. And another is L2 normalization. Okay, so these two are applied to columns of that pandas data frame, standard and min-max scaling, while this is applied to the row of pandas data frame. So applied to a single row or one record of the data set. Okay, so this is a completely different thing, and therefore I want to keep the word normalization reserved for when applied to a row, and scaling reserved for when applied to a column. And that way it will be easier for you to remember the code also. For example, this when you want to do a standard scaling, so at that time you will write that from sklearn.preprocessing import standard scalar to S are capital. Similarly, when you want to apply min-max scaling, then you will write from sklearn.preprocessing import min-max scalar again to M are capital. But here when you want to apply normalization to a row, previous two are applied to one column, while these two are applied to rows, then a single row. So at that moment you will write from sklearn.preprocessing import normalizer. So here import standard scalar, here import min-max scalar, while here import normalizer. Okay, so that's why I would prefer to use scaling only for this two two cases where the pre-processing is applied to columns of the data set, and I would prefer to use normalization only when the pre-processing is applied to the rows of the data set. Okay, now let us start this portion. So here that discussion starts. But if you see that in 12th chapter also we started the discussion from there only, and a lot of discussion would be repetition. So wherever things are being repeated, I will go through the whole discussion in a bit faster manner. But in this part we want to study this in even more depth also. So there will be some in-depth discussion. Now this is what is min-max scaling. I would cancel the word normalization mentally and write min-max scaling. So this is min-max scaling and this is standard scaling. As soon as you see, immediately you understand. We are not talking about the third one at present, right? So I told you that we want to discuss about three: min-max scaling, standard scaling, and L2 normalization or L1 normalization also. But we are at present talking about only two, these two, which are applied to column. So then this diagram is the best thing to remember. This right side is standard scalar and left side is min-max scalar. So what it does after scaling, that is what this diagram shows. So when you apply standard scalar to a data frame, then in every column, the mean of the column will be 0, and the standard deviation of the column, every column will have standard deviation 1. And similarly, when you apply min-max scaling, then every column will be converted such that the observations are between certain minimum value and certain maximum value, which you specify. But most of the time, we will specify 0 to 1. So that is what this red color diagram is showing, right? 0. So that is here, origin of the axis, and 1. Suppose this much distance is 1. So 0 to 1. That is called minimum value is 0 and maximum is 1. Alternatively, sometimes we will convert this into minus 1 to 1. So at that time, think that this is this vertical line, that is y-axis is shifted and it is above this dotted line, like this. Okay, so it is passing through the mean. So that means mean has become 0. So that means it is this kind of diagram actually. Think that way. And at that time, this would become minus 1. And I am assuming that this much distance is minus 1, and similarly this much distance is plus 1. So at that time, minimum value and maximum value between which my columns, all values will come, is between minus 1 to 1. So that is also called min-max scaling. So if minimum is 0 and maximum is 1, then it is called 0, 1 min-max scaling. And if it is minimum is minus 1 and maximum is 1, then it is called minus 1, comma 1 min-max scaling. Now why this standardization or normalization are, that is, I would say normalization word I don't want to use. So standardization and min-max scaling are required. They are required because this technique helps in scaling the data to a standard format, and it helps making it easier for the algorithm to process. Many machine learning algorithms perform better or converge faster when features are on a relatively similar scale and close to normally distributed. Two conditions are there for fast conversion and accurate model. One is that scale of various columns should be relatively similar. And second should be that each column's data, if you plot the histogram with a KD plot, then that should be, show roughly normal distribution. The best would be 100% normal distribution. Now, that scale of every column must be equal. What is the meaning of that? So let us try to understand. So we suppose here in this was the discussion about the label encoding in the previous lecture. So we are at present not interested in label encoding, but suppose I have taken this data set, right? That is same California housing data set, and these are its various columns. Now, if I write the statistical summary, then it becomes more clear. That is ds.describe. And if I write it, then it becomes more clear that ds.describe is this. So minimum value for the first med inc column, that is median income column, is 4.5 to $15,000 per month. House age is say 1 to 52 years. Average rooms are minimum 80.84 to maximum say 141. But all these three rows, even average bedroom also, they more or less are look on same scale. But consider this population. Now minimum value is 3, but the maximum value is 3, 5, 6, 8, 2. Now that is a pretty large scale. So this type of data set, if I directly feed it to the algorithm, and this can be fed to the algorithm because if I see the data types, all are numerical. So I can directly feed it to the some algorithm. But if I directly feed it to algorithm, then when I do the test and train and everything, then it will take a lot of time. Algorithm will take a lot of time to converge. Why? Because if you see the dimension of this data set, then you can see that it has 20,000 rows and 8 columns. So these are 8 columns, but 20,000 rows are there. So it is head is shown here. That is why only top 5 rows are visible, right? So then 20,000 rows, and then you will divide that into test set and the train set. You know that roughly around maybe 12,000 would be in the train set and 8,000 would be in the test set. Then second step would be you will train your algorithm. Suppose you have decided that I want to use the XGBoost. Then XGBoost on the train, X train and X test. That sorry, X train and Y train. So that means you will use only the train set for training. But that also will be 12,000 rows, and your algorithm will pass through that the entire data set, 12,000 rows in the training set for many iterations. Sometimes it will get the best possible accuracy, etc. when 100 iterations are over. Sometimes it may get when 200 iterations are over. So you can imagine that 12,000 rows and algorithm traverses to 12,000 rows from first row, second row, and so on up to 12,000 100 times or 200 times. Then it would make a lot of difference that if you can do something so that instead of that, the algorithm converges in just 50 iterations. So instead of 200 times passing through 12,000 rows, if I can do something so that algorithm has to pass only 50 times through those 12,000 rows of the train set, then it would be better. So fast convergence of algorithm means this thing. So here I have written many machine learning algorithms perform better and converge faster when features are on relatively similar scale. Unfortunately, here as I showed, population is not on similar scale. All other 4 features, first 4, are at least looking on more or less similar scale. But population is from 3 to 35,000. So very large scale is there, right? So then you have to do something so that all of these come out to be in the same range. And if you do, for example, min-max scaling 0 to 1, then what will happen? The minimum value of all the columns would be 0 and the maximum value of all the columns would be 1. Okay, so all are on same scale. Then your algorithm will converge very fast. Not only that, even the result obtained would be better. So performance of the model will also be better, right? Now normalization, which is better called min-max scaling. Again, better is written here because many people use word normalization for min-max scaling. That's why I have to write. But I personally do not prefer to use word normalization when I am doing something with the column wise to the data set. So I will prefer to use min-max scaling and standard scaling, right? So min-max scaling refers to rescaling the data features to the range 0 to 1 or minus 1 to 1, which is particularly useful for algorithms which are sensitive to input of data magnitude. And standardization involves converting the data to have a mean of 0 and standard deviation of 1. So this is min-max scaling on the left side, minus 0 to 1, okay? And this is standardization. Mean is 0 and the standard deviation is 1, right? So that is what this improves the stability and algorithm converges fast. Now, where such things are required is in some algorithms which are distance-based algorithms. So later on we will learn about k-means or k-nearest neighbor. As the name itself indicates, nearest neighbor. So nearest means some kind of distance. Near and far means some concept of distance would be there. Whenever some concept of distance is there, then if you use scaled data, that will give very good result for that. Okay. Standard scaling. So let us first do standardization discussion. Then we will do normalization or rather min-max scaling discussion, right? Okay. What is standardization? Standardization is converting each observation of a column, each value in a column to its corresponding z value. Now, what is the z value? That is observation value xi minus mu, the mean of that column, divided by sigma, the standard deviation of that column. A very simple example, suppose this is one column. Column, when I say, you should think that it is vertically distributed, right? 2, 4, 6. So name of the column is say X, and this first row has 2, second row below it has value 4, third row below it has value 3 in that column X. And suppose there are 10 rows like this. Now how to find the standard value of this X? Because clearly at present this is not standard. Standard is what? This is standard. Mean should be 0 and the standard deviation should be 1. Now here all values are positive, so their mean can never be 0, right? So what you will do for doing that? 3 steps. First step, calculate the mean of given column, then calculate the standard deviation of the given column, and then calculate the Z score for each observation, which is given by xi minus mean divided by standard deviation, where mean and standard deviation you have calculated in the previous 2 steps, right? So if you calculate the mean in this case, then that would be sigma xi divided by n, or sum of all this divided by n. So if I find it, it would be 5. Similarly, if you calculate standard deviation, that is sigma xi minus mean whole square divided by n. So if you find it, that will be, here xi are these values. So 2 minus mean is 5 square plus 4 minus mean is 5 whole square, and so on up to last number is 3 minus mean is 5 whole square, and sigma of that. Sigma means between each term I have to take plus, and then that is this term in the numerator, sigma xi minus mu whole square, right? And divide by number of observations. So that would give me the sigma xi minus mu divided by whole square n, and then take the square root. So that would give me the standard deviation, that is this term. So each observation minus the whole column's mean value you have to do, and then square it, and sum of all such squares and divided by total number of records in that column, or total number of rows in that column. That would give standard deviation for that column. And once the standard deviation and mean are obtained, then I can use this formula, xi minus mu divided by sigma. So that means value of that observation minus the mean, which you have found here 5, divided by sigma, which you have found here 2. So then first observation is 2. So 2 minus 5 divided by sigma is 2. So that is first Z value. Second is 4 minus 5 divided by 2. Third is 3 minus 5 divided by 2. And similarly, last 2 will be 8 minus 5 divided by 2. And 3 minus 5 divided by 2. Okay, so each observation minus the mean value divided by standard deviation. And if you find this each Z, then you will get one this kind of list. Minus 1.5, minus 0.5, like that, right? So that list will show you that X was originally not standardized. This was not standardized. Not standardized means it did not satisfy this property that the mean of all these would be 0 and the standard deviation is 1. But now this Z of X, that is Z score of the X, that satisfies this property. If you find the mean of all these, then it will be 0 because each positive value will cancel the corresponding negative value. And if you find the standard deviation of these observations, then it would be 1, right? Okay. Now then, similarly, this is column Y, other column. Now this time I had taken, here I had taken 2, 4 such small scale values. This time I am taking large value. Okay, so 1000, 4000 and so on up to 5000. Again the method remains same. First calculate mean, sum of all observations divided by number of observations, 10. Okay, so that is 4000 is the mean. Standard deviation. Now here standard deviation calculation would be a lot long. So that is the yi minus mean mu y divided by, sorry, whole squares, and then sum of all those yi minus mu y whole square terms, and then divided by number of observations. So first let us find this each yi minus mu y whole square, all those terms, right? And for that I will shift this below so that you can see. Okay, so this was my y, right? So then, or I think that y is already there, so maybe it was good at original place only. Okay, so this was good at original place only, right? And here y is already visible here, and these are also y visible in each Z score, right? So now I can find this 1000, that is the value of y, minus mu is 1843 for y column, that is the mean of that, divided by standard deviation of that is mean is 4000 for that column here, here 4000 y column, yeah, mean of y, and standard deviation is 1843. So then if you find that, then you will get the you will get the Z score for each observation. So that would be 1000 minus 4000 divided by 1843, and 4000 minus 4000 divided by 1843, 3000 minus 4000 divided by 1843. In general, the method would be same, that is yi minus mu y divided by sigma y, or observation minus the mean value of that column divided by standard deviation of that column y. Okay, and if you find that score, then this will be the Z score. You can see that the original values were pretty large, but the Z score for that large value also comes out to be more or less same order as the order of X Z score was there. Zx was also of the same order, right? Now then you can find this, I think this is just getting repeated, no? This should not be there. This is just getting repeated, right? So these are the Z scores, okay, for these observations, correct? These observations, right? And if you find the mean of this, then it would be 0, because again each positive value would cancel the corresponding negative value. Say this plus 1.09 and this minus 1.09, this plus 0.54 and this minus 0.54, and this plus 1.63 and then minus 1.63. So mean will be 0 and standard deviation would be 1. So that is according to this diagram, and that means that you will say that my y column has now been standardized. So this is original y column and this is standardized y column. Okay. Now this is standardized y column. Now what I can do is I will paste these values, and I will check if same thing is obtained or not by code, because now here this is my zx, so which I got. Now let us see if I get same value of zx and zy using this kind of code. So code is very simple. I start with two lists and convert them into pandas data frame. I initialize standard scalar for which I have imported from sklearn.preprocessing import standard scalar. Two s are positive, right? Sorry, capital uppercase, right? So this s and this s, they are uppercase. Okay. So then initialize a scalar object, and next step is scalar.fit transform on the data. So this is my data set, and I will do scalar.fit transform on the data, right? So these steps are just the same. If you see that label encoding steps, then we import label encoder here. Here. So we import label encoder from sklearn.preprocessing import label encoder. Similarly, an L and E are capital. Similarly, there we will import from sklearn.preprocessing import standard scalar, where S and S, two S are capital. Then we will create an encoder object LE equals to label encoder. There we can create an object, say SS or scalar or whatever name you want to give to that. That is just the name, is equal to standard scalar. Then you apply that LE here, LE dot fit transform on my data or the column. If you can apply to entire data frame also, or you can apply to any individual column also. Exactly similarly, here also you first import standard scalar, create a scalar object. Okay, because data creation is fine, data will be actually be already given to you. So import standard scalar, create a scalar object from here, directly jump here, then just apply that. So that is scalar.fit transform. Just like there you write le.fit transform, here scalar.fit transform, and to entire data set, right? If I take this much to the next cell just for better understanding, then in that case, and here I just print my data frame, then my data frame is like this, x and y, 2, 4 up to 10 observations, and 1000, 4000 and so on up to 10 observations. That are the same values, and now I'm checking whether when I apply standard scaling, my data frame becomes like this or not, right? So I have imported my standard scalar, I have initialized the scalar object, and I now apply that scalar object to my entire data. This is my data. So then apply so scalar.fit underscore transform to my data, and store that in where in a new data frame, standardized data. Okay, and then that unfortunately this scalar has one limitation, that when it gives the output, it will not be a pandas data frame. And this is important, remember, because sometimes errors arise because of this small thing. So it will not be pandas data frame type. And if you want to do what type this object is, then you can write type of and in bracket standardized data. So it will not be pandas data frame. So you have to convert it back to standard data frame with the columns which you want to give. So original data frame had column X and Y. So I want to give the new data frame name X standardized and Y standardized. Or I can also give this simple name Z underscore X and Z underscore Y. Z score of Z value of each observation, right? And then combine the original data also and standardized data also, so that I can compare that. For which I will use pd.concate. These two columns X or this data is the data frame which gives my original data, and this result DF, sorry, standardized DF, that gives my data after scaling has been done, right? So standardized data is this after scaling has been done. Okay, and I have converted that into the data frame. So I will concatenate the two data frames with axis is equal to 1, so that they will be concatenated one beside another. So that means this original data frame had two column X and Y, and this will have two column X standardized and Y standardized, and the final result data frame would have 4 columns. So before you execute the code, please cultivate that habit with Jupyter Notebook, that before you just go on press, if you just go on pressing next, that thinking will not develop. So before you execute a code, you just think what should be the output and then press next. So you can see this was my original X result data set, and this is the statistical summary also I am printing. Okay, so X, Y, X standardized and Y standardized. If I see that X standardized and Y standardized, that is these Z values, then you can check whether you are getting proper answers or not. I am taking still below. Okay, so these were my values. So X standardized means this ZX. Okay, so here this X standardized. So minus 1.372 and so on. So that is minus 1.5, somewhat closer to those values, right? Exact value you will not get, but you are getting somewhat similar value. Y standardized is also minus 1.63, so 1.52, 0.54, 0.10, and so on, right? So that is how the values are obtained. Now you can do this, check this describe statistical summary. This is the output of this line, print result ds dot describe, right? So that is this output. And if you see the mean of x standardized, then the mean of this x standardized is 0, because it is 4.44 into 10 to the power minus 17. So that is 0.000016 zeros and then 444, which is nearly 0. Okay, that much inaccuracy comes because of the calculation in floating point number, which has some limitation of accuracy with computers. And similarly, this y standardized its mean, if you find this is the mean, okay, in the statistical summary, so y standardized its mean is 0.000016 zeros and then 333. So in short, both means are 0. Now standard deviation. So this next line is the standard deviation, and this has 1.054 into 1, or that is 1. Okay, and this is also 1.054, 10 to the power 1, 10 to the power 0, 10 to the power 0 means 1. Okay, so both have standard deviation 1 and both have mean nearly 0. So that is exactly what I needed. If I see my standardization diagram, then mean should be 0 and standard deviation should be 1, right? Okay. So this is about standardization. Now same thing I can do for actual data set. That was the data set which I had created, x and y, but now this is for actual data set. So California housing data frame you can take, and instead of, okay, first let me execute that. So fetch California housing, and that will be fetched as a data. This is not a pandas data frame. Again, if you want to know what is its type, then you can write type of like this, type of, and in bracket data. Let me even do that for you in the next cell, then I will delete that cell. So you will see that it is not a pandas data frame. Type of is not defined. Why? Or type data, I think. Yeah, not type of. Right. So it is sklearn.utilities.bunch.bunch. So that means it is some kind of specialized data form which the sklearn library has given, but you have to convert that into pd.dataframe, and at that time you will write data.data and columns data.feature names. Even those two also you can check what each gives. For example, data.data, and if I execute, that will give me the various columns, and data.feature underscore names. So data.feature underscore names. If I do that, then it will give me the number of names of the columns, right? But now this is so common, but you should remember one important limitation of sklearn often is that even after label encoding, or even after this scaling, it particularly after scaling, it does not give data in the pandas data frame form. Similarly, if you load any ready-made data set from sklearn library, then it will not be in the form of the pandas data frame. So you have to convert it into pandas data frame. So this is the step which converts it into pandas data frame. And then let us print the statistical summary of that. And I am adding one cell. Why only statistical summary of all? But I mean one column only. But I am printing statistical summary of all the columns, because then only it will be clear that it is required to scale or not required to scale. So that shows that the minimum value is here, looking on more or less equal front, and these are also looking more or less equal, but this has minimum value 3 and maximum 35,000, so requires scaling, right? And then you can do from sklearn.preprocessing import standard scalar. Same steps every time you have to do, and then create a scalar object, standard scalar. So this is now just an object which is created, but then you have to fit it on either entire DS3 or any particular column of DS3. So suppose I want to fit it on house age column, then I am fitting on house age column, and then now you describe that column, you will see a visible difference. Now the mean is 0.000017 zeros and 55. So that means mean is 0 for all practical purpose, and the standard deviation is 1.00024 into 10 to the power 0. 10 to the power 0 is 1, and this is also 1, right? So it is again converted into a mean value of 0 like this, and standard deviation equals 1. So I have shown standardization by definition for a simple data set like having x and y only 2 columns, this type of data set, and then by code, then I have shown standardization or standard scaling for my entire data set also, right? So then this is what the standard scaling means. Ultimately, the mean should become 0 and standard deviation should become 1. Okay. In next lecture, we will talk about min max scaling. Thank you.